Alright, let's delve into the world of linked list operations. So, these operations allow us to perform various tasks with linked lists, a fascinating data structure we have been exploring. So, in this section, we are going to focus on the fundamental operations that can be performed on linked lists. These operations help us manage and manipulate the data within the linked list efficiently. Let's take a look at them. First, we have traverser, which involves accessing each element of the linked list. This helps us examine and work with the data stored in the list. Next, there's insertion, a key operation. It lets us add a new element to the linked list, and this is essential for expanding the list and accommodating new data into the linked list. Then we have deletion, which removes existing elements from the linked list. This operation is crucial for maintaining the content of the list. Search is another operation. It allows us to find a specific node within the linked list. This is useful when we want to locate and work with particular data. Lastly, there's sort. This operation helps us organize the nodes of the linked list in a particular order, making it easier to work with the data. So, let's go over some important points to keep in mind about linked lists. First, we have the concept of head, which is like a signpost. It points to the very first node in the linked list, helping us start our journey through the list. Then there's the next pointer. This is like a path leading us to the next node in the sequence. But here's a trick. When we reach the last node, this pointer points to something special. It points to null. This tells us that there's no further node to move on, and we have reached the end of our linked list adventure. Now, let's look at a specific example to get a clearer picture. Imagine we have a linked list with 3 nodes labeled as 1, 2, and 3. Each node has a structure that holds 2 strings. Its data, which is the number it carries, and next, which is the pointer to the next node. So, if you think of it like a train, the data is the passenger's ticket, and the next is the next station where the train is headed. Remember this structure as we are going to use it in our examples. Alright, so with these concepts in mind, we are ready to dive deeper into linked list operations. So let's continue our journey. Let's understand how to traverse or move through a linked list. Imagine you have a train of nodes, each carrying a number. To see all the numbers, you need to walk through the entire train, right? So traversing a linked list is just like that. Here's how it works. We start at the first node, which is called head. This is like the starting station of our journey. We create a temporary node, let's call it temp, and make it point to the same station where the head points. So our journey starts at the beginning. We are going to take a look at the contents of each station. For example, at the first station, we note down the number it holds, which might be 1. Then we move to the next station by following the next pointer. We keep doing this until we reach a station where there's no next station, meaning our temp has become null. This indicates we have reached the end of our journey, or the end of the linked list. Now, let's look at a piece of code that does this. This C++ code segment initializes a pointer temp to the head of a linked list. Then iterates through the list using a while loop. Inside the loop, it prints the data of each node followed by an arrow as a separator and updates the temp pointer to the next node. The loop continues until the end of the linked list is reached. Here, temp is like a passenger who walks through each station, and when temp becomes null, our journey is completed. So, if your linked list has the numbers 1, 2 and 3, this code will display an output like this. And that's how we are traversing a linked list to see all its content. Let's dive into adding elements to a linked list. Think of our linked list as a train where each carriage has a number. Now, we will learn how to add new carriages with numbers. There are 3 ways to do this. First, adding to the beginning. It's like adding a new carriage right at the front of the train. The new number becomes the first one and the old ones follow. Second, add to the middle. Imagine you want to insert a new carriage between 2 existing ones. It's like adding a new number in the middle of the train. Third, add to the end. If you want to extend the train, you just add a new carriage at the very back. So, depending on where you want your new number, you will use one of those methods. Remember, each carriage has a number and a pointer to the next one. When we add a new number, we adjust the pointers to make sure the train is still connected. So that's how we insert elements to a linked list. Let's learn how to add a new element at the beginning of a linked list. Imagine you have a train of numbers and you want to add a new number right at the front of the train. So here is how you do it step by step. Step 1 is allocating memory. You create a new train carriage or node for the new number. It's like finding an empty carriage for your new passenger. Step 2, store data. You put the new number inside the carriage. This is the value you want to add to the linked list. Step 3 is change pointers. The magic happens here. You make the new carriage's pointer point to the carriage that was at the front before. In other words, you connect the new carriage to the old front carriage. Step 4 is update head. Finally, you update the front of the train. The pointer that used to point to the old front carriage now points to the new carriage. So the new number becomes the new front. So if you put this in code, it would look like something this. And just like that, you have added a new number to the beginning of your linked list. Let's move on to adding an element at the end of a linked list. Imagine you have a train of numbers and you want to add a new number right at the back. Here is the process broken down. Step 1, allocate memory. You prepare a new train carriage or a node for the new number. It's like getting a new carriage ready at the end of the train. Step 2 is store data. You put the new number inside the carriage. So this is the value you want to add to the linked list. Step 3, traverse to last. Now you need to find the very last carriage in the train. You start from the front and keep moving from one carriage to the next until you reach the last one. Step 4, change pointers. Once you are at the last carriage, you change its pointer. The pointer that was pointing to nothing, which is null, now points to the new carriage you just created. This connects the new carriage to the train. If you put this in code, it would look something like this. And that's how you add a new number to the end of your linked list. Let's understand how to insert a new element in the middle of a linked list. Imagine you have a sequence of numbers and you want to slide in a new number right between two existing ones. Here is the process explained step by step. Step 1, allocate memory and store data. Just like before, you create a new carriage or node for your number. Then you put new number inside the carriage. Step 2, traverse to the right spot. Now you need to find the carriage just before where you want to add the new one. It's like finding the two carriages you want to slot your new one between. You start from the front and move through the carriages. Step 3. Change pointers. Once you are at the right carriage, you change its pointers. You make it point to your new carriage and you make your new carriage point to the carriage that used to come after the one you are inserting in between. This effectively inserts your new carriage in the middle. So if we translate this into code, it would look something like this. That's how you insert a new number right in the middle of your linked list. Alright, let's delve into how you can remove elements from a linked list. Imagine you have a list of items and you want to remove one item. It's like taking out a piece from a puzzle. Here is the breakdown of the process. Deleting from the beginning. Just like how you start solving a puzzle from the edges, you can remove an item from the start of the linked list. You change where the front points to, effectively skipping the first item. Deleting from the end. Similar to finishing a puzzle and removing the last piece, you can remove an item from the end of the linked list. You change the pointer of the second to last item to point to nothing, effectively disconnecting the last piece. Deleting from a particular position. This is like removing a specific piece from the middle of the puzzle. You find the two pieces you want to disconnect and you make the one before point to the one after, effectively removing the piece you want. Delete from beginning. This is similar to take the first piece from a line of puzzle pieces. Here is how you can do it using code. In this C code segment, a pointer temp is initialized to the head of a linked list. The head pointer is then updated to point to the next node in the list. Finally, the temp pointer, which originally pointed to the old head, is freed using the free function. This sequence of operations is often used to remove the first node from a linked list. Delete from the end. It's like taking the last piece from a line of puzzle pieces. Here is how you can do it using code. This C code segment is removing the last node from a singly linked list. It starts by traversing the list until temp points to the second to last node. Then it creates a pointer last node to the last node, updates the next pointer of the second to last node to null, effectively disconnecting the last node from the list. So finally, it frees the memory allocated for the last node using the free function. Think of it as carefully removing the last piece of a puzzle and then making sure the previous pieces doesn't point to it anymore. Delete from middle. It's like taking out a specific piece from a row of puzzle pieces. Here is how you can do it using code. This C code segment is removing a node at a specific position in a singly linked list. It starts by traversing the list until temp points to the node immediately before the node to be deleted. The for loop runs until the desired position is reached. Then it creates a pointer, which is node to be deleted, to the node at the specified position, updates the next pointer of the previous node to skip the node to be deleted, and finally frees the memory allocated for the node using the free function. Think of it like carefully removing a specific puzzle piece from the middle and then making sure the pieces on either side connects seamlessly. Search an element on a linked list. Imagine you are looking for a particular toy in a row of toys. Here is how you do it in code. This C code defines a function search node that searches for a node with a specified key value in a linked list. It takes a pointer to the header of the list, which is head_f, and an integer key as parameter. The function iterates through the linked list using a while loop, checking if the data field of the current node matches the key. If a match is found, the function returns true. Otherwise, it continues iterating. If the end of the list is reached without finding a match, the function returns false. Think of it like going through a line of toys, checking each one to see if it's the one you are looking for. If you find it, great. If not, you keep moving down the line until you have checked all the toys. Let's talk about sorting a linked list, like arranging your toys in order. We will use a simple sorting method called bubble sort, and here is how it works in code. In this C code, it defines a function sort linked list that performs a simple bubble sort on a linked list. It takes a pointer to the head of the list, which is headref, as a parameter. The function uses nested loops to iterate through the list and swap data values for adjacent nodes if they are out of order. The sorting is done in place, modifying the linked list directly. The function handles the case where the input list is empty. Think of it like comparing toys and swapping their positions to get them in the right order. We keep doing this until we have gone through the whole line of toys and they are all arranged from the smallest to the largest.